everyone, and welcome to our final mapping module, Spatial Analysis in Veterinary Epidemiology. Today, our focus is on identifying, measuring, and interpreting spatial patterns. In earlier sessions, we learned how to build reliable spatial databases and how to create descriptive maps. But estimating the true level of disease in a population requires more than mapping. It requires understanding how individual factors, place, and time interact. We keep asking the same questions. Where is disease unusually common? Where is it unusually rare? And what is different about those locations? In this lecture, we move beyond simply viewing maps and start analyzing them statistically. We will learn how to test whether a cluster is real, how the key formulas work, how to model environmental risk, and how to use results to guide field action. Let us begin with the basic spatial distributions seen in veterinary practice. Before we apply complex mathematics, we must understand the basic spatial distributions seen in nature. When we map an outbreak, we are plotting a series of disease events, and the first step is to describe how they are arranged in space. A random distribution would mean the underlying risk is uniform across the landscape. This is uncommon for infectious diseases. A clustered pattern is the most frequent. It often suggests a point source exposure or local transmission spreading between nearby herds. A dispersed pattern, where cases are more evenly spaced, may reflect strong territorial behavior in wildlife or management practices that reduce close contact and limit clustering. Early maps are descriptive and are usually created without a formal hypothesis. Even so, they are essential. They guide our thinking and provide the foundation for the analytical studies that come next. A key rule in epidemiology is that we cannot rely on our eyes alone. The human brain naturally looks for patterns even when data are random. If you scatter a handful of feed on the ground, you may still perceive clusters. For this reason, visual clustering is never enough to justify a disease control action. We must move to analytical studies that formally test hypotheses about the link between an exposure and an outcome. In spatial analysis, this means hypothesis testing. The null hypothesis is usually that disease events are randomly distributed across the landscape and any apparent clustering is caused by chance. We then calculate the probability of observing a pattern like this if the null hypothesis were true. Only with that evidence can we confidently inform decision makers that a specific area represents a true hotspot. To show clustering statistically, epidemiologists use measures of global spatial autocorrelation. This idea reflects Tobler's first law of geography. Locations that are close to each other tend to be more similar than locations that are far apart. In veterinary epidemiology, it captures spatial dependence. In other words, the infection status of one farm may be influenced by the status of nearby farms. A global spatial autocorrelation test looks at the entire study area at once. It asks, across this region, do farms with high disease rates tend to be located near other farms with high disease rates? This is a key first step. If a global test suggests the pattern is random, there is no strong scientific reason to run advanced hotspot detection methods. We first need evidence that clustering exists at the landscape level. The most widely used statistic for global spatial autocorrelation is Moran's I. Let us walk through the logic of the formula in simple terms. The calculation compares how disease values vary across neighboring locations using a spatial weights matrix. For each farm, we look at the difference between its disease rate and the overall average rate. We then multiply that difference by the same difference for a neighboring farm. If a high incidence farm sits next to another high incidence farm, the result is positive. If a low rate farm sits next to another low rate farm, the result is also positive. All these cross products are summed to produce Moran's I, which usually ranges from -1 to +1. A value well above 0 indicates clustering. A value near 0 suggests randomness. A value below 0 suggests a dispersed pattern. While Moran's I is widely used, epidemiologists also apply another global measure called Geary's C. It is important to understand how it differs in practice. Moran's I compares how values deviate from the overall mean and then looks at how those deviations relate across neighboring locations. Geary's C, in contrast, focuses directly on the difference between neighboring pairs. The formula sums the squared differences in disease rates between nearby farms. Because it uses squared differences, Geary's C is more sensitive to strong local variation than Moran's O. The interpretation is also different. Geary's C usually ranges from 0 to 2. A value of 1 indicates complete spatial randomness. Values between 0 and 1 suggest clustering or positive spatial autocorrelation. Values between 1 and 2 suggest dispersion, meaning neighboring areas are more different than expected by chance. Global statistics like Moran's I and Geary's C can confirm that the whole country or region shows clustering, but they do not tell us where the clusters are. For outbreak response, we need local spatial statistics. A common tool is LISA, which stands for Local Indicators of Spatial Association. You can think of LISA as a local version of Moran's I. It breaks the global measure into location-specific results, producing a separate spatial autocorrelation value for each farm, village, or county in the dataset. We then calculate a p-value for each location to test whether the local pattern is unlikely to be due to chance. This lets us map exactly where spatial dependence is statistically significant. In practice, LISA turns a regional summary into a practical targeting tool, helping field teams focus investigation and control measures on the most important areas. When you run a LISA analysis, the software groups each statistically significant location into clear epidemiological categories. A high cluster means a farm with a high disease rate is surrounded by neighbors with high rates. This often marks the main outbreak focus. A low cluster means a farm with a low disease rate is surrounded by low-rate neighbors. This suggests a lower risk area or a spatial sanctuary. LISA also highlights spatial outliers, which are especially important for field work. A high-low outlier is a single farm with a high disease rate surrounded by healthy neighbors. This is a major warning sign. It suggests the infection did not spread through local neighbor-to-neighbor contact. Instead, it may point to an external introduction, such as an infected animal moved in from another area. In practice, this finding triggers targeted contact tracing and a focused biosecurity investigation. Another widely used spatial statistic in veterinary epidemiology is the Getis-Ord Gi tool, pronounced GE star. While local indicators of spatial association focuses on how a location relates to its neighbors, Gi star focuses on hotspot intensity. The method sums disease values within a defined local neighborhood and compares that local sum to to what we would expect based on the entire study area. It produces a z-score and a p-value for each location. If the local sum is much higher than expected, the z-score becomes strongly positive, indicating a statistically significant hotspot. If the z-score is strongly negative, it indicates a cold spot. This tool is especially useful for area-level data such as county incidence rates, when you need clear statistical evidence to justify which counties require urgent control measures, including quarantine and movement restrictions. One of the most robust and widely used cluster detection methods in public health and veterinary epidemiology is the spatial scan statistic developed by Martin Kulldorff. In earlier lectures, we noted that administrative borders, such as county lines, can bias interpretation. Kulldorff's method avoids this by using a moving window that sweeps across the landscape. At each location, the window changes size to include different numbers of farms or people. The algorithm repeatedly compares the disease rate inside the window with the baseline rate outside the window. This allows the analysis to detect the natural biological footprint of an outbreak without being constrained by political boundaries. The window that produces the strongest evidence of elevated risk is identified as the most likely cluster, and it becomes the primary focus for investigation and control. How does Kulldorff's scan determine whether a window contains a true cluster? It uses a maximum likelihood ratio test. As the window moves across the map, the method calculates two probabilities. The first is the probability of observing the data if a real cluster exists inside the window. The second is the probability of observing the same data under the null hypothesis, meaning the disease is randomly distributed. The formula compares the number of observed cases inside the window, the number expected inside, and the number outside. The window that produces the largest likelihood ratio is flagged as the most likely cluster. Because many overlapping windows are tested, standard p-values are not suitable. Instead, the software uses Monte Carlo simulation. It generates thousands of random disease maps and compares them with the observed pattern to estimate a final p-value. Traditionally, the spatial scan statistic uses a circular window. This is computationally efficient, but it can be unrealistic because most biological patterns are not circular. For example, if a waterborne pathogen spreads along a winding river, a large circle may include the river. However, it may also include many healthy farms far from the riverbanks. This can dilute the signal and overestimate the area at risk. To address this, modern spatial epidemiology uses flexible scan statistics. These methods allow irregular window shapes that can follow real terrain and connect adjacent areas based on true geography, not just distance from a center point. The result is a cluster that better matches the likely transmission pathway while reducing false inclusion of nearby but unexposed locations. Disease does not exist only in space, it moves through time. To capture this, we use the space-time scan statistic. Imagine taking the spatial scanning window and adding height so it becomes a three-dimensional cylinder. The base of the cylinder is the geographic area and the height represents time such as days, weeks, or months. The method searches for groups of cases that are clustered in both space and time at the same moment. This is especially important for identifying a propagated epidemic. In a propagated epidemic, one case infects others, and those new cases then infect additional cases. This often creates an epidemic curve with successive peaks. The space-time scan helps us detect and follow that spreading pattern, showing where and when transmission intensified as it expanded across the landscape. After scan statistics show us where clusters are located, we still need to explain why they occur. This is where risk surface modeling becomes important. We use analytical methods to test hypotheses about the link between an exposure and a disease outcome. The aim is to clarify parts of the web of causation by examining how host, agent, and environmental factors interact. By entering known risk factors into a spatial model, we can build a predictive risk surface. This turns a map of scattered infected farms into a continuous heat map. The heat map estimates the probability of disease for any geographic coordinate, even in places where cases have not yet been reported. With this approach, veterinary services can shift from reactive response to proactive surveillance and targeted prevention. The main statistical tool for building predictive risk maps is spatial logistic regression. Standard logistic regression is used when the outcome is binary. For example, a farm is either infected, coded as 1, or not infected, coded as 0. The model estimates the log odds of infection based on one or more risk factors. However, in spatial data, farms are not independent. Because of spatial autocorrelation, nearby farms often share similar risk. If we apply standard regression, uncertainty can be underestimated and p-values can look more convincing than they should. Spatial logistic regression addresses this by adding a spatial term to the model, often described as a spatial error term or spatial random effect. This adjustment accounts for the influence of neighboring farms. When we build spatial regression models, many of the covariates we include come from the environment. Disease patterns in space are often shaped by climate factors such as temperature, humidity, and rainfall, and by management factors such as grazing practices or housing systems. We can extract these variables from raster layers and link them directly to farm locations for modeling. At a more advanced level, we can use ecological niche modeling. This approach describes the environmental conditions a pathogen or its vector requires to persist. For example, it may define the humidity and temperature range needed for a specific tick species. We then scan the wider landscape to find areas with similar conditions. This helps us predict where disease could establish if it is introduced. For veterinary authorities, this supports early warning, targeted surveillance, and better preparedness. Up to this point, we have treated locations as fixed coordinates shaped by local environment. But farms are not isolated. They are connected through trade and animal movement. Network analysis helps us map these connections. In this framework, each farm is a node, and each movement or trade link between farms is an edge. These movements explain how disease can jump long distances and bypass local clustering. A pathogen may travel 300 kilometers in a single day on a livestock transport vehicle, creating a new cluster far from the first detected farm. By combining network analysis with geographic information system data, we can trace contact patterns and estimate where transmission risk is highest and where spread is most likely to occur next. This supports targeted tracing, surveillance, and control. Within an animal movement network, not all farms or facilities play the same role. Some livestock markets or dealers have far more connections than others. We measure this using centrality metrics. A highly connected node can act as a major transmission hub if infection is introduced at the right moment. From that hub, movements may distribute infection to many regions in a short time. By combining network analysis with geographic information system data, we can identify which locations are most connected and therefore most influential in disease spread. This allows veterinary services to prioritize surveillance, tracing, and temporary movement controls at key hubs. Reducing movements through highly connected nodes lowers contact rates across the network and helps bring transmission under control. As we generate these complex spatial statistics and p-values, we must maintain our clinical grounding. There is a dangerous tendency to equate statistical significance with medical importance or biological relevance. Small differences of no real interest can be statistically significant simply because the sample size of animals or farms is massive. Furthermore, if your spatial scan software evaluates 1,000 different circular windows across a region, pure chance dictates it will flag statistically significant clusters that are entirely fake. This is the multiple testing minefield. When you identify a spatial cluster with a p-value of less than 0.05, you must step back and ask, is this difference significant and certainly large enough to be of practical importance? If a cluster does not alter our epidemiological understanding or our disease control response, its statistical significance is irrelevant. The ultimate goal of all spatial analysis is to implement effective disease control interventions. Once a causative spatial pattern is assessed, measures can be applied to reduce the level of exposure, reducing the rate of disease in the population. If our LISA or spatial scan identifies a cluster, we use that geographic footprint to establish targeted vaccination zones or cull test positive animals. We use our spatial models to draw buffer zones and movement restriction areas. For example, if we utilize Moran's eye and LISA to uncover a statistically significant cluster of FMD near a wildlife reserve, our intervention plan involves drawing a strict buffer zone around that exact hotspot, restricting cattle movements, and initiating targeted surveillance. We use spatial analysis to ensure our field veterinarians are exactly where the predictive risk is highest. Thank you for your attention throughout this module.